Welcome everybody to our webinar today. I am Allison Herrera. I'm an account manager here at Summit Interconnect, and I'm going to be moderating this webinar. So first of all, I want to go through some of the logistics. If you haven't been on one of our webinars, there is a control panel at the bottom of your screen, and you can find there an area where you can chat. So any of the questions that you want to submit, it's an interactive webinar, so you can just submit your questions there to the chat. And then if we're able to, we're going to answer those questions throughout the webinar. And then we'll also have time for questions at the very end. This is also being recorded, so there will be a copy of the webinar sent out to everyone that's registered at the end of the webinar. So we have a special topic today, which is, let me read it so it's the correct topic. So we're discussing how to match today's manufacturing technology to your PCB project. And we have two special speakers. We have Chris Hunrath, who is an accomplished technology leader with over 3 decades of experience in the electronics industry. He is currently serving as the Vice President of Technology at Insulectro, and he has been instrumental in supplying critical materials for PCB manufacturing. Prior to Insulectro, Chris provided technical sales and support for plating and process chemistry at OM Group, and his career has also included significant roles in equipment engineering and chemical process engineering. Chris is consistently demonstrating his commitment to advancing technology in the electronics sector. So that is our first speaker, and our second speaker is Mike Trammel. Mike Trammel is a seasoned professional in the electronics manufacturing industry, currently serving as the Director of Product and Technology Transfer at Summit Interconnect. With more than 35 years of experience, Mike has played an important role in advancing Summit's high-quality manufacturing capabilities. His extensive background includes Business Development Manager at Insulectro and Director of Engineering at DDI, where he led process engineering teams and implemented lean manufacturing practices. Mike has consistently driven innovation and growth throughout his career. So we want to welcome both of these men to our webinar today, and I'm going to go ahead and pass it off to them. So welcome, Mike and Chris.
Yeah, so Mike and I have co-presented in the past.
Yeah.
And I always start off saying, despite our appearance, we're mostly harmless. So mostly harmless. Anyway, Mike, go ahead, talk about the agenda today.
Yeah, so we're going to talk about some of the new innovations, that we're seeing in the industry. It's kind of neat working in this industry because we continue to innovate and we get challenged in new ways every day, and our equipment and chemical and material suppliers have responded well to what the customers are asking for. So and I like it here. We at Summit, we've got a management team that's committed to capital expenditures, trying to stay ahead of the curve, and to meet not only today's needs but the needs coming up in the future.
Yeah, so Mike and I have worked together a long time. I remember one project we did, gosh, it might have been 15 or 20 years ago, where we took for a special customer project, we took automotive refrigerant leak detector and mixed it into the legend because they wanted a legend that would glow under UV light. So we've done some interesting on-the-fly special projects for customers over the years. But anyway, we're going to talk about some of the things that are converging from manufacturing to materials to design. There are some things that are coming together, including the equipment set, that are opening up some opportunities for advanced PCBs. So I don't know, Allison or Lisa, if you want to take this one and talk about Summit a little bit.
Yeah, I can do this one. So Summit is the largest privately held PCB manufacturer in North America. We have 8 different factories throughout North America. We can support everything from prototype, quick turn, all the way to flight-ready production PCBs. We also provide assembly, and we have pretty much whatever type of design that you can come up with. We have somebody that can support you to help you get that design better and make it manufacturable. And if you need a quote or help with a project, please reach out to us. So we offer a complete portfolio of PCB products. We offer rigid boards, rigid flex, special materials for RF and microwave, like Rogers, Isola, EMC, a lot of different variety of technology, cavity boards. So semiconductor, obviously. So whatever kind of project that you have, if you need a home for that project, we have a facility that will support you.
I'll just take this next one, a little bit about Insulectro. We support fabricators like Summit with everything from materials to equipment, process chemistries, on-site support. We're doing more and more connected factory, which Summit has been one of the pioneers on that, where we have chemical process monitoring that goes to the cloud, but also sends real-time data if something goes out of spec. So we're just trying to advance that technology, but we're real excited to be working with Arlon and EMC. They bring a lot of R&D and materials, new materials to the industry that some of we'll be talking about today. So hopefully we'll find some interesting topics for your PCB needs and designs, and we can advance that. So with HDI and what we call ultra HDI, which is sort of a moving target. In other words, what's HDI today, won't be HDI tomorrow. But with some of the things that are coming together, whether it's the low CTE dielectrics, the low loss dielectrics, the new imaging technology, which Mike's going to talk about, plating technology, and of course some of the new photoresists. These things are all converging and opening up some really nice opportunities as we build PCBs. So classically, especially on interlayers, we do a subtractive process. Basically, you take a core, you apply a photoresist, and you print and etch. Now, that technology has advanced, and Summit has some new equipment for that. But there's also an opportunity to do what we call semi-additive. And just to put it in perspective, board shops are doing semi-additive today. Sometimes that gets conflated with substrate technology, but when you're doing outer layers on a PCB, you're starting with a thin foil, you're putting on a photoresist, and you're going to pattern plate holes, vias, and circuits all at the same time. Doing what we're talking about today is just extending that to the next level with some of the new photoresist equipment and foils that are available. So really the difference is with semi-additive is you're creating a mold for the plating, whereas subtractive, you're creating a mask for the etching. And this just shows the outcome. And one of the things you can do with a photoresist that you can't do with chemistry is chemistry can't go through the copper. I mean, it's etching the copper, removing it, but light can go through the photoresist and form a feature that is very, very straight sidewalls, but also can be very, very small depending on the capability of the resist. So you can do things with resist you can't do with copper and etch. So we're going to have a little video right now. Let me see if I can get this to go right. All right, there we go. Talk about some of the new exposure technology. There we go.
Hi, my name is Mike Trammel, son of Santa Clara. Welcome to Tech Spotlight. Today we're going to be talking about a new imaging system that we brought in, upgrading and displacing some of the older technologies. What you're going to see in the room today is essentially state-of-the-art, leading edge. I'm going to talk a little bit about how this new machine sets apart from one of the older machines I'm going to show you right now. So this is a small PBI-CT very, very fast. It's going to run about 130,000 an hour. It's supposed to be about 7 on the older system. Much higher resolution, faster, so we can do sub 50 microns or 6 dial technology on this at a very, very high rate. It's also very versatile. You can run this was dedicated to Interconnect. We've also got a program for soldering mask and computer as well. It's part of our automation initiative. And next time you see in the video, we have two robots taking it and left the So again, that's control, how we get these. Another system we find in plant. The CB tech. Also a direct image system, you see why it's supposed to be here. This one's specified specifically for solder guns. It's about 3x the speed of our current or prior system. Very, very fast, also very, very accurate. Good to about 50 microns as well. We're actually competing both velocity, so we're kind of looking at our own solder gun. Brand new, right off the assembly line. This machine is just installed. We'll have an introduction to a lot of things.
So this is the outcome of that equipment. Mike, do you want to talk about that for a sec?
Yeah, so it's pretty amazing. This is using standard dry films. We're actually in the middle of testing, even going past these current stated capabilities. The good news was when we tested, it actually exceeded the stated capabilities, and I think that's kind of the German engineers do that on purpose. They understate and over deliver. But yeah, very, very satisfied. It's met all the requirements from an imaging standpoint, and Chris and I are now working on using some of the higher resolution films that we had qualified on, that prior laser technology as opposed to the direct image technology. And pretty excited to see where it goes. But our anticipation is that we're gonna be doing 20 micron on a regular basis.
So one of the techniques we use to qualify the imaging process, and that's really to set the exposure and develop of the photoresist, is to tin flash a part. And what's nice is we can do this on a sample part, or really any copper clad core, and make sure we have the imaging just right before that we actually apply that to the production board. So we tin flash and then strip the resist. You can see an example here of where we neck down the traces to 25 micron for the BGA fan out. We're going to talk more about that and have a live example coming up in a few slides. But it's a real nice technique to qualify both the exposure unit, the photoresist, and the developing process to make sure everything's just right before you get into production.
And I think that's the key is, it's as we implement these new processes, it's, one tends to outrun the other. So, I put in new imaging, then I have to put a new develop etch strip to be able to, develop and etch that. And then even after that, we need to upgrade our AOI systems to even be able to detect those smaller traces. What we're looking at here is this is a project that Chris and I worked on together. This is the new UCE develop etch strip line that we implemented here in Santa Clara. And based on the huge success we saw here, we immediately rolled one out to our Toronto factory. We're cutting a deal for 2 more of these to go into, I believe, our Orange and Hollister facilities to bring that technology to all the shops. And again, Chris can talk a little bit about the technology, but I'll just state, so I'm a numbers guy. I look at data, and I've qualified maybe 40 etchers in my career. And I pulled the data using the same spreadsheet and surface mapping that I do for all of them. And I thought I must have dropped a 0. So I completely redid the testing and got the same result. So this is, essentially 100x better than anything I've ever profiled in my prior career. And that's a lot of etchers. So, but Chris can talk a little bit about the, why it's, why that's possible and the technology that makes that an enabling technology.
Yeah, so vacuum etching basically puts a vacuum bar right after every spray bar in the etch process. And what that does is it prevents the puddling you get from the etch spray from solution sitting on the surface. That gets you very consistent etching from the edge to the center of the panel. Because if you didn't have that, you'd end up either under etching or over etching certain tracks on the board. And when you're going with finer lines, they all have to be the same. Because again, if you have, let's say, a 12 micron variance in your line width on 1/2 ounce copper, that's okay on 100, 125 micron track. But if you're going down to 50 or 30 microns, to have that 12 micron variation, it's just not viable. So the vacuum etch, again, the idea of vacuum etching isn't new. The difference is this is in production, it's here right now, and it's producing, as Mike pointed out, very, very good results. So copper foils continue to advance. I know copper foil sounds very mundane, but I get a ton of questions on copper foil from the fabricators and even designers and OEMs because they care about things like surface treatment, the RZ topography for high speed. But one of the things we want to talk about today is some of the advancements in carrier foils. Carrier foils have come a long way, and that allows us to make some very thin foils, almost at the level of where you would do, say, substrate technology, where you would do a electrolysis layer, and then you would image and then do your buildup that way, your electrolytic copper that way. What's nice about the carrier foils is it's infinitely scalable. You can do 4 panels or 400 panels. It just doesn't matter. It's just a matter of applying the different foils. So as I mentioned, foils have become a big issue. There's a big variety right now, but we have some new foils, some that are very, very smooth for high frequency. And also, again, the new carrier system with the release liner or the release treatment allows us to do things we couldn't do before. The old carriers were in risk of fusing into the functional foils. So it's very common to have a 1/2 ounce carrier that you can peel off after lamination.
And I know this, it used to be very, very simple. You had 2 or 3 choices from a foil standpoint, but don't let it confuse you. Between Chris and I and our pre-engineering team, we're very well versed on the different applications, the possible pitfalls, and the expectations. So, if you want to talk about foil, make sure that if you're specifying a foil and you're not sure, please, give one of our pre-engineers a call.
Yeah, so you'll hear terms like HVLP, VLP2, and other terms. They have different meanings from different suppliers. So the IPC has become a little bit better in specifying it. The new spec, one of our teammates is on the 4562 committee. These are going to be the new designations for the foils, but even within those designations, there is a variety. So again, as Mike pointed out, that's something we can help with. But HVLP might mean 3.1 micron for one supplier. It might mean a maximum of 2 micron on another supplier. So again, that's an area where we can help. So as I mentioned, 1/2 ounce peelable carrier. The release layer technology is improved. It used to be, depending on the lamination temperature, if you were 350 Fahrenheit, it was no problem. But as soon as you went above that, you had risk of the foils fusing together, and then you couldn't remove the carrier. And now you're stuck with a 1/2 ounce plus instead of the ultra thin foil you wanted. But we do stock 1.5, 3, and 5 micron. And again, coming up, we have an example of what the 5 micron could do for you in an advanced design. So just some images of a 1 millimeter pitch, a 0.8 millimeter pitch. One of the things that we'd like to talk about is partial or part-time HDI, where you're not trying to build a substrate. You're doing a PCB. It might be an advanced PCB, but it has a BGA with a footprint that might be something less than what we're normally used to. And one of the things you can do is you can neck down that trace. So 2 examples here. All the routing's internal in this one. There's no VN pad. In this one, you have a 0.8 millimeter pitch with 4 mil or 100 micron traces. Pretty standard for a BGA route or fan out on the inner layer. But this does open up some opportunities where you can neck down the circuits without really a loss in transmission line performance, as long as that neck down is short. And really the rule of thumb is as long as it's less than 1/4 of the rise time, you can do that neck down in the BGA fan out, where the rest of the board's conventional density, but you have that ultra high density just in the BGA area.
And again, this is where it takes that very specific equipment set and standard etching technology. you just can't maintain that neck down. You end up, to get your standard trace widths to the correct width, you end up over etching because of the distribution of the etch. You end up over etching those neck downs. With the new technology, Chris is going to show you an example where we can do that.
So this is something that's actually been produced by Summit. In fact, Mike, you had some cases where you've done down to 30 microns in a fan out, right?
Yes.
So, but this is a 50 micron example where a 100 micron circuit is neck down to, I like to say condensed, down to the 50 micron to accommodate a 0.5 millimeter pitch. And this technology can be extended even further than this. It's a combination of the photoresist, the exposure unit, the etch capability, you know, and of course, you know, the rest of the processes. When you're doing multiple layers like this, let's say you're doing a sequential lamination buildup, that's where the dielectric materials become important because they have to have the right properties to make all this work. So as I mentioned earlier, we're really excited to be working with EMC and Arlon. They have an extensive R&D department, and they are really focusing on not only the speed of the transmission line properties of the materials. They're really focused on making sure the CTE is low. So when you have bulk resin areas that are filling in between these traces, that you know you get the right type of reliability.
So Chris, in case there's entry level people, can you explain what CTE is?
Yeah, coefficient of thermal expansion. So PCB materials, especially rigid PCB materials, a little bit more than flex, are composite materials. And the coefficient of thermal expansion is usually measured or rated on the material on its glass and resin combination. What can happen in some of these advanced designs is you can have areas where you have a lot of bulk resin, and that's where the resin of the pre-preg or laminate has to have the right properties.
And that's where we're starting to push, you know, the design, you know, the standard design limitations of the past, where you know you don't want to stack over, you know, your best feature or your best architecture would be, you know, single micro via stagger, single micro via stagger, and then we move to the, you know, one micro via stacked onto another, then over, and then repeat, rinse and repeat. But now we also have a software program where we can actually test the capability. It's called Gauss. So we do these Gaussian analyses, and it's like things that we thought would never even, you know, do a 10 lamination cycle board with micro vias in it. You know, in the past, it's like that's just a no bid. But now we're actually seeing and building these. And again, it's all because we're using these new advanced materials that not only have the high speed electrical properties you're looking for, but the low CT allows us to make these smaller packages a reality.
Yeah, so you can vet the design by changing the material properties based on the different laminate systems, and vet that before you go to production.
Exactly right.
So these are some of the new materials that we offer. And I do want to point out that Summit's run all of these. 4 out of 5 of these, I would say, are qualified, and one's been run with you know, normal results, but just hasn't been run in a larger way. And that's the 892K. That's a relatively new material compared to the others. And while Summit's run it, they haven't run a ton of it, but the other materials they have experience with.
So what's the big difference between 890 and 892K? I know it's for them.
Yeah, so it's lower loss. It's even lower in loss, and it's lower in Z-axis CTE. So it's just an improvement over the 890K. The K designation for the EMC materials designates low decay glass. So if you need that 3.0 decay space where you're trying to build a PCB that might have been on a fluoropolymer system, you know, a Teflon type system, you could use these materials because they'll match both the DK and DF, or the dielectric constant and loss tangent.
Yeah, and that's and not necessarily just the EMC products, but there's other FR4 or reinforced fiberglass type materials out there that are now chasing the same electrical properties as Teflon. And from a cost standpoint, it's just you're gonna get a higher yield. You don't have all the we won't go into too deeply, but Teflon's, very, very difficult to process internally. Nothing sticks to Teflon. So again, if you don't need that extreme, that extreme electrical property requirement of Teflon, and if these numbers work for you, we strongly recommend that you move to this type of material. It just makes the build so much easier.
Yeah, especially if you're doing stacked vias and HDI buildup, it's just a whole lot easier using materials. These fit comfortably in a PCB fabs manufacturing environment. And actually, there's a new material called 86HP that Summit's also run, and it's a unique polyimide chemistry with substrate like CTE.
Yeah, we're about 10 data points short of doing a complete release on that. All the current testing, we've actually built a few production jobs. Looks very, very positive.
So why is all this important? As I mentioned, when you're doing stack vias and HDI buildup, you end up with some areas where you have a lot of bulk resin. The fiberglass tends to tent the copper features, and then the resin from the prepreg will fill those areas. If that resin doesn't have the right properties, you'll actually blow these via structures apart. Again, Mike mentioned simulation software. It takes all that into account. Copper is low in CTE, so compared to resin in the Z-axis. So just as a sidebar, regular epoxy, its coefficient of thermal expansion is 150 parts per million. It's the fiberglass and sometimes the filler that bring that down. But there's things you can do with the resin chemistry to bring that down even further. And that really makes these structures buildable and viable. So here's just some good examples. This is a filled system, and you can see the filler particles in it, but you can see the fiberglass fabric has basically tented or bridged the copper areas. So wherever you have copper circuits, you're going to have what we call neat resin. And here's an example of an unfilled system. But you get the idea. You end up with a lot of this resin. Now, if you're stacking vias and you're electroplating each one of your layers to fill your vias, blind vias, you're going to end up with relatively tall copper structures where you're going to have a lot of bulk resin in those areas.
Something that's really not covered in this presentation, but it's another consideration is, I don't know if we talked much about mechanical drilling, but that's the other thing is, as these filled materials came into market, we had to develop some very specific drilling parameters for these. It took a little engineering, but that's been overcome. This is essentially standard product for us today with our new drill systems.
So EM370Z is one of the new materials that I talked about. It can be used for everything from thick copper to stacked vias. It is an epoxy system. It's a very economical system. It's not necessarily a low loss system. It is lower than the phenolic cured epoxies. Phenolic cured epoxies became very popular when lead-free assembly for commercial took hold in the industry around 2006. So phenolic cured systems were a way to get FR4 to meet the new lead-free temperatures. The 370Z is not a phenolic system. It is an epoxy system, but it's an upgrade from the phenolic systems, and it can be hybridized with the low loss systems.
Anything else on that? I just want to make a comment. So for you designers out there, that picture is for an example. From a design standpoint, we can build that, but you really don't want to do three microvias stacked on top of a thermal like that. And at the now we are doing 3 stacked vias that are passing to us with this new material, but we would still discourage you from stacking right on top of that.
Yeah, this was a test vehicle just to see the limits of the material.
Yeah.
But 370Z it's great for high voltage. It's great for electric vehicles. It's an economical, high reliability FR4 system. It's even being evaluated because it's halogen free. It's the burn products are being evaluated to see if they're lower toxicity for things like aircraft cockpits and areas where if you had a circuit overload, you don't want to create any kind of nasty fumes. So that's actually being tested by an OEM.
And to be clear, that structure did pass the IRE flow 260C times 10 cycles. So not saying we can't do it, but we do have ways to test your designs.
Yeah, you guys have design rules that
Yep.
and
we also
promote best practice.
We also have that Gaussian software we can take your design and once we know what material you've specified, we can actually either give you an idea of what your success rate would be, or if we need to recommend a different material.
But for economy, you can do a hybrid with 370Z and something like 890K, where you have the high-speed circuits or F circuits and the 890K material, but the rest of the PCB is on something like 370Z to save overall cost. So just a little bit more about the new 86HP. It's a new material. It's a polyimide that just has some advanced filler and chemistry technology, where the DK and DF have been reduced over standard polyimide, but very, very low coefficient of thermal expansion, not just in the Z-axis, but also in the X and Y. So just some examples of what you can do with the material, whether it's a ultra thin HDI buildup, or it's something more conventional where you have four stacked vias over a 14 core.
Yeah, and this is another. So these thinner prepreg offerings that are relatively new to the industry, it's another one of the enabling technologies. So first you have to have a factory that's capable of handling that thinner material. Also the learning the fill characteristics and the scaling characteristics. So that's something that any factory needs to get under their belt before they can even consider these, like that 727 structure you see on the left hand there.
Yeah, automation and thin core handling is very, very important for that. Just some examples of the 86 HP, some of the structures that can be built with it, whether it's a buried via or stacked vias, and then of course the thermal reliability after some exposure to whether it's cycling or reflow cycles, thermal cycling or reflow cycles. So for some of the advanced HDI, there are some films out there that have been used, but what we're finding is that for fabricators, they're very used to dealing with prepreg, the glass reinforced prepreg. We now have offerings of prepregs that are in the film range in terms of thinness, and you could use these in combination with the more standard building blocks to build some advanced stacked via HDI boards. So really nice. And again, this goes back to the technology where, you can imagine, if anyone's familiar with prepreg manufacturing techniques and of course laminate manufacturing techniques, what it's like to handle half mil fiberglass fabric. It takes advanced treaters to be able to do that. But again, it's something that the fabricators are comfortable with. They're used to this kind of technology. They're not having to work with some of the films that aren't reinforced, that need a carrier all the way through the process. This is much more conventional, just more advanced.
So now that we've moved into these new advanced technologies, how do you know that it's actually working? And something that's been developed through IPC, and specifically this is the conductor analysis guys, but it's OM testing or decoupon testing. So if you're just venturing into some of these newer design aspects, if you really want to qualify a design, we strongly recommend a decoupon testing. It will vet your design and your material selection and flow selection.
Now you guys can do this in-house, right?
Yeah, so we have OM testers in several of our facilities. We do this in-house, and that's the nice thing too. If you're dealing with a supplier that doesn't do this, you might want to consider another supplier. Only because we don't have to say that we're good. We have empirical data based on this decoupon testing that only says that that our structures are very, very viable and strong. It also vets your design. So if you have a very specific design that's pushing the limits, we can model it using the Gaussian, and then we can prove it out.
And you've had good correlation with that simulation software to the OM results, right?
So far, so good. We're going to talk a little bit about embedded resistors. I think there's only one supplier now, Omegaply bought Teicher, right?
Right. So there's two technologies. One is to use a nickel phos film on the backside of copper foil. Another technology uses various alloys that are sputtered onto the backside of copper foil. And then that copper foil then is laminated, and then you selectively etch and strip The primary sputtered alloy is nickel chromium, but they do have some other resistor value films that produce higher ohms per square. But basically, it's a selective etching process. Basically, you etch everything, including the resistor layer. Then you come back and etch your copper off where you want to form the resistors. So you can see the sequence here.
Yeah, and again, I have pre-engineers that are well versed in this process. Again, we follow the standard. There's a very basic design guideline on how to build these. If you have a specification or you want to specify embedded resistors or any embedded passive, actually, we do have a whole design group that's, again, we build these at several shops, and we're well versed in this technology as well.
Yeah, so typically the resistor layer is represented by this gray film. So you'd etch the copper, etch the resistor layer, then you'd come back and photo image, and then just strip the copper off of the resistors. So really the only thing bridging your circuits in this case would be the resistors. And then this is what a panel might look like. This, of course, is a test panel, but it has a lot of different examples. You could see this large resistor. They like to say that the resistor material is dimensionless. In other words, if it's ohm per square, it could be anything you want. But if the width and the length are equal, you're going to get whatever that ohm per square is. So let's just say, for instance, it's 100 ohms per square. If I make the width half the length, then it's going to be 50 ohms. I'm going to cut the resistance in half. If I make the length twice the width, I'm going to double the resistance, and so on and so forth.
Yeah, and if you get stuck on doing the math, we'll be happy to help you with it.
So Ormet paste is a way to join layers in the z-axis. It's also been used for embedded components because once the paste is sintered, it doesn't remelt. But it is a way to create z-axis interconnects. The paste has some unique properties. It melts at one temperature, and then once it forms a new alloy, the new melting point's much higher. So the initial melt starts at like 130 Celsius. We like to process at 190, but once that alloy is formed, the new melting point, one phase is 415 Celsius, the other is 650. So it just opens up some different technology possibilities in either bonding layers together or bonding subs together.
And we've got several of our shops are qualified for this, specialty application. But we actually have an Ormet center or paste center. No pun intended. You can tell what centering is, right? But yeah, so this centering paste.
So you have a center.
Yeah, SINTER CENTR, but that's down in Orange County. We have a full workshop dedicated just to this technology. So this is another specialty application. We generally build these out of our Toronto shop. And again, it's for thermal handling. Another way to handle this is doing like a microvia farm or, farmed vias. But this is a quick and not easy way. And again, we kind of push these over to Toronto because they're really, really good at it. But in a nutshell, you take a copper slug and you can either drop it into a sublayer and microvia down to it, or alternatively just attach it, all the way through the board. But very, very good for thermal handling. As you know, copper is very electrically conductive and thermally conductive as well.
All right, we're going to just wrap up with some automation.
So as I stated, we've got a automation initiative. The next time you see that video that we began with, we're going to have a full set of robots.
The EVTA 650 is an inline desktop automation for loading and unloading machines, such as LDIs, AOIs, and inkjets. It can also function as a standalone solution when combined with a 2-servant or MOV 650 slot rack loader or unloaders. The two 3-axis robots enable a pick, place, and flip of the PCB and allow an A or B mode for a one pass-through operation. Multi-batch and multi-format handling is integrated through an automatic gripper, which allows the recognition of various panel sizes. All settings can be saved as recipes for quick access and reenactment at a later time. Due to the sleek design, unlimited access is granted to all machines for easy maintenance. The EDTA 650 is the fastest system of its kind on the market, operating at a cycle time down to 10 seconds per side. It has a uniquely small footprint and only consumes 800 watts. This automation is compatible with most LDI, AOI, and inkjet systems, and can be linked to a manufacturing execution system, allowing traceability and unique handling per PCB. The EDTA is a valuable addition towards fully automated manufacturing.
So as stated, we've got an automation initiative, here at two other factories. And again, next, if you join us in a future webinar, we'll spotlight that automation system on that same the Schmoll TTG unit, all the way from pre-clean through code, all the way through the development strip line that we showed. So it's going to be a no touch from beginning to end.
Yeah, so as we mentioned at the start, again, materials, equipment, the needs for BGA fan out and tighter pitch, these are all kind of converging. So I think it's a good opportunity to open this up for questions. I don't know if Allison or Lisa, you've seen any questions out there?
Yes, so we have one question so far, and it is, what is the BGA routing partial HDI neck down deployment driven by? Is
It's
it
really
by
BGA footprint and the fact that new components are coming out for certain markets and that need the smaller footprint, but they're being utilized in other markets as well. So it's really the component industry is driving that, and the markets they're serving is driving that footprint.
Yeah, and additionally, if we can support these finer pitch structures, you can eliminate layers. So right now, using standard technology, you need more and more route out layers. As we miniaturize in the X and Y, you can remove some of the Z-axis requirements, adding a layer for routing, et cetera, like things like that. Additionally, too, if you're in the design mode, we do have some design guidelines available for 0.4 millimeter and below. But again, if you think about it, when you reach that technology, if I'm able to support even a 0.25 millimeter pitch device, it just makes the larger pitch devices easier to support.
So another question is, what slash sheets would these materials fall under?
So some of them are 130. Some of them are, I want to say 134. The 86 HP actually is a slash 40 and 41 material.
Okay, so there's
yeah, sorry, go ahead.
Oh, there aren't any other questions yet, but just for one question, I was wondering, when you're talking about the fine pitch, and are you talking about MSAP, or is it just starting like with a thinner foil and doing the traditional outer layer, using the tin resist, or is it something totally different? Kind of what you're describing at the beginning.
Yeah, so actually there are multiple options. Certainly you could use something like ASAP, where you're starting with a very thin electroless copper layer and then build it and then imaging it and then plating up. Really it's a matter of degrees. Foils are nice because they're, like I said, they're scalable, they're easily scalable. They don't bring you the same level of density that an ASAP process would. But if you don't need 8 micron features, or 12 micron features, if you're in the 25 to 30 micron space, it's very easy to use something, let's say, more conventional for the PCB fabricator and using a foil.
Yeah, and again, that's the key word, more conventional. The more conventional you specify, the less money it's going to cost you. The alternative technologies that are, just now being advanced, are generally very, very expensive from a capital expenditure standpoint.
Yes. So,
Yeah,
so you could use tin as an etch resist, or if you start with a very thin foil, you can actually just flash etch. And really it depends on what level you need in terms of that BGA neck down.
Okay. So one question, the person saying, I've heard some OEMs talk about maximum of 3 stacked micro vias with the preference being staggered. What are you hearing? And is there any consensus or just application driven?
I'm going to let Mike answer that, but I can tell you that staggered has always been considered best practice. What we've done with the new materials is extended the range.
Yeah, so if you look back, it's always been, and there's a lot of white papers and data out there, but it's all based on the prior, call older material types. So the standard rule is, and again, this still applies from a reliability standpoint, because here's the kicker. Summit can build just about any structure you specify. You saw some of the pictures, but we're not going to recommend that unless we've got some data that supports it. So the best practice recommendation is a single micro via stagger, and you can't see me drawing lines in the air, but you zigzag through the package. So one down stagger over, one down stagger back. That's your best practice recommendation and will be the strongest. The second one used to be, micro via 1 to 2, micro via 2 to 3 stacked on top of each other, stagger over, and etc. Now we're seeing these structures that would have been an absolute no bid prior with these new low CT materials, and again the micro via technology, and also these thinner dielectrics that are now offered. We can reduce that aspect ratio, which also makes it stronger, easier to fill. So we don't really know what the number is. We've been challenged, but we've gone as high as, I think, we've gone 6 high, and we're actually successful. But again, if you're not clear, I mean, those are your best practice rules. But we can't exceed those, but it's very, very specific. So if you send us your design and you send us the material specification, we can analyze that for you and give you recommendations on exactly what to do.
Yeah, I think really in summary is, stagger is always best practice, but because of room and density, sometimes you're forced to stack the vias instead of staggered, and the new materials make that feasible. I think that's the best way to sum it up.
Another question is, what % of the market production do you believe is at this technology level versus what you might call standard technology? And how fast do you see this growing?
So that's the highest growing market sector. Rigid, flex and rigid flex took a huge jump in 22, 23. We're starting to see a lot of, aerospace and defense customers utilizing more flex and rigid flex, and and another thing that drove them, they use the same chips the commercial jobs do, so they're being driven by pitch too. A lot of that was these even using flex type materials in a rigid package to try to get there. This is a more eloquent way to solve that. So right now it's probably the fastest growing market sector, and more than 40% of what we build here in Santa Clara anyway is of an HDI with at least one or two layers of microvias.
Yeah, I think really the component industry is going to drive this, and I think that's going to accelerate. And I think when designers get accustomed to the capabilities that are now coming from the fabricators, automation, the new equipment, the exposure equipment, and the new materials, I think that'll open up, a lot of opportunity to expand this technology.
Yes, so there's another question. It's not related to picking a substrate, but do you have any design guides available for your common board stack-ups, or perhaps some reference DRC rule sets for common design packages for Altium, Cadence, etc.? And I can kind of answer that. We do have, design rules, and we have common board stack-ups that we can share. But as far as related to this emerging technology, I'm not sure if it really captures that. I don't know, Mike, if you...
So, yeah, so we have our standard design rules. We also have a 0.4 millimeter pitch fan out guideline. And we also have presentations on the MSAT process as implemented in Summit.
Yeah, you saw
Okay.
some of that in the presentation. And, you know, I think the best suggestion is if your design is pushing the limits, you know, have a conversation.
Yeah, definitely. Because I was going to mention, you know, if a lot of this stuff, if it just comes to the quoting team, it just comes to sales, you know, it might get no bid, or it ends up going to review. So a lot of times I think that if someone is designing this, they know that their design includes this type of material. It's best to just call up their account manager, you know, let them know that they've seen a webinar where we discussed it, and then that'll get them on the right fast track to talking to somebody like Mike that can help them, you know, get their design quickly through that process. And because a lot of times I know for us on the account manager side, when there's some of this that we see and we don't know that someone's seen this webinar, or so kind of, I think it's important to have that conversation with your account manager that you know, seen this in a webinar or presentation, then that'll help connect you to the right person that can get it, you know, faster through that quoting process and through engineering to get their project, you know, taken care of. Yes, if that makes sense.
Yeah, it's part of the purpose of these kinds of webinars, right? Is to
Mhm.
let people know what's going on out there.
Yes. Okay, so another question, are you seeing more widespread adoption of conductive adhesives replacing solder? And is that driving substrate technology in a certain direction?
I'm not seeing it in the PCB world. We do support printed electronics at Insulectro because we're all about electronic materials, and that's typically, you know, lower technology. It could be wearables. It could be you know, it could be membrane touch switch. It could be you know, things like glucose test strips. We see conductive adhesives in that industry a lot. I don't see it in PCB. I don't know if the Summit folks have.
Yeah, so I see the occasional ask. It's less than 5% of the ask. Almost everyone is using you know, standard assembly technology. I have seen conductive adhesives, not only electrically but thermally, products being used for adding what's the word I'm looking for? Heat sinks and things like that. So yeah, so they're out there, but again, it's probably less than 5% of my ask.
Mhm. Okay, so I don't see any more questions. So I suppose to conclude, if we will be sending out this presentation recording to everyone that has registered for the webinar. And then if you have any particular questions beyond that, I encourage you to reach out to your account manager, or you can go to our website and get started there, and we'll connect you with the appropriate account manager that will help you get the answers that you need. And if you have any special projects that kind of fall under these guidelines, that's the best place to start too. If you don't have an account manager, then go to our website and put in a request, and then we'll connect you with somebody that can help you get the questions answered by Mike and Chris. And we want to thank everybody for joining us today. We do these webinars every month, so keep an eye out on your email, and we will be sending out the next one soon.
Great. So Allison, Lisa, thank you so much for putting this together. We always enjoy you know, showcasing, you know, our technological capabilities. So thank you so much for putting this together, and for those of you that attended, thank you so much for your time.
Yeah, thanks, ladies. Thanks for everyone who listened in.
Yes. Okay.